Hi, everyone. Good afternoon. I'm Don King, and you've just met my colleagues, Lotfi, Hermie, and Craig Sutton. And I'm going to try to explain a little bit about the explorations in spectral geometry that we are pursuing and to motivate some of the important problems in this area. Next slide.
Yep.
So we start with a problem or situation I'm sure many of you have seen, and certainly a very important problem or in partial differential equations. We have a planar region in R2, omega. We can think of omega as a drumhead, and we're interested in understanding the displacement of this region as you beat it with some object. And we call that displacement u of x, y, t. So this displacement function satisfies so-called wave equation, second partial of u plus the Laplace, plus an operator times u is equal to 0. And we assume that the boundary of the drumhead remains in the plane. So we have what I'll call the mathematician's Laplacian minus the sum of the second partials with respect to x and to y. And we'd like to understand that function. And so there's an old method, I don't know exactly to whom it's due, of so-called separation of variables. And what we find is that this Laplacian has a sequence of eigenvalues, which we denote lambda 1, etc., up to lambda k. And we also are able to derive in this setting the eigenfunctions, the phi sub k. And it happens that they have these numbers and the functions have certain properties, one of which being that the eigenfunctions form an orthonormal basis of the L2 space of omega. So as I said, using separation of variables, we get this well-known expression for u of x, y, t involving those eigenvalues and the trig functions, cosine square root of lambda kt and sine of square root of lambda kt. And these, the quantities that you get from these eigenfunctions give us what's often called the natural frequencies of omega. So this is an important example to keep in mind because we can generalize that. Next slide. Next slide, please.
Oops. Oh, I think we went to the next slide.
Okay. So one of the things we're interested in is the relationship between the spectrum of the operator nabla and the geometry of the region that we've been given. We can also look at the special distribution, trace of e to the minus t times the operator. And we find that it has a very interesting asymptotic behavior in which the two lowest terms involve the volume of omega and the length of the boundary of omega. So this is the case in which we're getting important information about the physical situation from the terms in this asymptotic expansion, the so-called heat trace. Next slide. So in general, you get some kind of information from the eigenvalues and eigenfunctions, but you don't get enough information to entirely determine the shape of your drum. And that's often expressed by this statement that you can't hear the shape of a drum. But still, it suggests that there will be relationships that do give you at least some information. Let's look at the next slide. So one of the things we'd like to do is be able to generalize our results for this so two-dimensional or three-dimensional example to more general manifolds. And I mentioned that the proper setting for this is to look at a compact Riemann manifold, M, and its metric, it's G, and to generalize the constructions that we had in the planar case. So first of all, we can define a Laplace operator in the indicated way. And what we obtain is an operator that is self-adjoint from L2 of M to L2 of M, and which has a spectrum of eigenvalues. Again, so we'll denote this by lambda 1, et cetera, lambda k. And we get, and in principle, we have eigenfunctions. Now that may not be so easy to write down explicitly, but certainly these are general facts. And we can again ask the question, what does our spectrum of eigenvalues tell us about the geometry of a more general Riemann manifold? Next slide. So in general, we will find that a Riemannian manifold MG is not determined up to isometry, because that's the relevant thing here, via its spectrum. Nevertheless, one expects that for some spaces, we should have some kind of rigidity. In other words, the eigenvalues should tell us something about the space we're looking at. Next slide. So let's take a general compact manifold M with boundary, or excuse me, without boundary, and look at and try to say something about the space of Riemannian metrics on M. So one of the things we can look at is the extent to which the given metric is deformation rigid. So in other words, if we introduce a small parameter, t, positive real t, we can ask whether the spectrum that you get from G is the same as that which you get by this deformation. If not, if you can't do such a deformation, then you call this deformation rigid. Next slide. We also want to know the extent to which having, knowing the set of eigenvalues picks out G in a very precise way. I won't read the definition, but the point is we want to know to what extent our eigenvalues are picking out a special metric. And let's just go to the next slide. Well, I think there's a little more technical details than I want to get into, but I think the point is that we're trying to see to what extent our eigenvalues allow us to identify G specially. Now, for me, this is kind of brand new, and the case I'm mostly interested in is when you have a manifold that has some kind of action of a compact Lie group, because that's really where I'm coming from, the representational theory of Lie groups. And so I'm particularly interested in situations where you have a manifold that has the Riemannian metric, but that also has a group action under which the metric is preserved. And there are many examples of such. In particular, one is having a compact simple Lie group itself. So if you have a compact simple Lie group such as the special unitary group in SU2, then it turns out that on any compact simple Lie group, they're left invariant metrics, and they're bi-invariant metrics. And the bi-invariant, so you have an action of G on the left and the right. Those metrics are very special. And if you compare a bi-invariant metric to just a left invariant metric, you will see that it's distinguished by that fact. And one of the things we're trying to do is to see whether we can formulate a generalization of this result, which is due to Craig. And so we're going to be very interested in the coming week in looking at situations in which you have bi-invariant metrics versus left invariant metrics for more general manifolds. So thank you for your attention. I'll stop there.